Welcome back, everyone. So we're continuing with nodal analysis. We're going to do a slightly larger problem than last time. So let's go ahead and let's start. We're going to have a combination of current sources and voltage sources in this specific problem. So let's give ourselves a 12-volt source. A 3K ohm resistance. A 6K we'll put a current source over here going in the direction to the left by conventional current. It'll have a value of 2 milliamps. Over here we'll have a 2K ohm resistor, and we'll have a 4K over here at the top. So here's a great example where nodal analysis is going to allow us to solve this, and we really couldn't solve this too many different ways. Okay, so we're going to start off with, let's do our step number one. Step number one, let's go ahead and assign the reference node. And I'm going to try and pick the reference node someplace on this circuit to call 0 volts that makes sense to me. Now, I could put it over here, and you could solve it that way. There's nothing wrong with placing the reference node over here, or over here, or over here. However, because I have the negative side of my 12-volt source over here, and yeah, I'm just going to place my reference down here. Okay, so we're calling this point 0 volts as the lowest voltage of our circuit for the sake of writing out our expressions, our equations, and then solving that system and then finding out what our voltages are. Okay, so that's step one. Step two, we're going to go ahead and label all non-reference node voltages. So every point in your circuit where you have a voltage that's different than 0 volts, we're going to go ahead and label it. Now, the first one that stands out to me is over here. I'll call this V1. Okay, I have a voltage drop across this 3K. So let's go ahead and call this point V2. Now notice all along this wire is V1, all along this wire is V1, all along this wire to the 12-volt source is V1. Same thing for V2, it's V2 all along here. Along a wire, the voltage is the same at every point. So there's only a need to label this point that covers all three of these wires coming from this node. Okay, this over here is going to be a different voltage. We have a current source here and a voltage drop across this resistor and this resistor. So this is the last place that we need to go ahead and assign a non-reference node voltage, and I will list that as V3. Okay, perfect. So that takes care of step two. Step three, let's go ahead and write out these expressions. Okay, let's go ahead and do the first one. What is the first one? Well, notice the first one's pretty straightforward and easy. I don't have to assign any currents. I don't have to write KCL. If my goal is to write out the voltage, well, V1 is equal to 12 volts. Easy. All right, let's move on to V2. Okay, V2 is going to have a little more work to do. V2, let's see here. I'm going to have to write out some currents and then write out a KCl expression. So I'm going to try and pick some currents for here. If they make sense to pick them to go in a specific direction, I will. Otherwise, arbitrarily, I'll pick them to go in any direction. So let's go ahead, and the first thing that stands out to me along this wire here, I have a 2 milliamp constant current source. So I'm going to draw my conventional current to go in the same direction as my current source, and let's label that as 2 milliamps. Okay, along this 6K, I have ground referenced on one side. I have 0 volts here. So I'm going to make the assumption V2 is higher than 0 volts and just say that this current is going down. And over here, I can pick this to go in any direction. It's not going to make any difference whatsoever. I'll just pick it to be leaving. Okay, now let's go ahead and label these currents. I'll pick this one to be IA. I'll pick this one to be IB. This is just interim work for the sake of writing out KCl and making this problem a bit easier. So now I can see that if I look at Kirchhoff's current law, I have 2 milliamps entering and IB and IA leaving. So I can say the sum of all currents entering a node must equal the sum of all currents leaving that same node. IA plus IB. Do I have something underneath my board? No. I have a little bit of a teetering going on with my clipboard. Maybe I need a new clipboard. Okay, so we now have our KCl expression for this node at V2. Let's go ahead and write out what IA and IB are. IA is the easier one over here because I only have the voltage drop across 6K, which is V2. So I can say V2 divided by 6K, just invoking Ohm's law, will give me what IA is equal to. And I'm done with that. Let's go ahead and express IB. IB, little more complicated, or shall I say we need to pay a little more attention to this guy because I have the current going from V2 to V1, so I'm working off of the assumption that V2 is higher than V1. Well, current always goes from a higher voltage to a lower voltage, so I can say plus V2 minus V1 gives me my voltage drop across the 3K. So IB is going to be equal to V2 minus V1, and all of that is the voltage drop across it, so I can take the voltage drop across it and divide by 3K to invoke Ohm's law and give me what IB is equal to. Now we can go ahead, plug all this back into our original expression, and we get our second equation. So let's go ahead and say that IA plus IB is equal to 2 milliamps. So I'll say V2 divided by 6K is equal, plus V2 minus V1 divided by 3K is equal to 2 milliamps. And I'm done with my second equation. Okay, so I got 2 equations. I got one left to write. Let me go ahead and split up my board just a little bit. For writing out this third equation so we can all see everything at the same time. Okay, let's go ahead and write out that third equation. To do this, I'm going to have to draw in some currents. I'm going to try and make the currents make sense to me, at least try to keep it as consistent as possible with my, let's see, with how I've already picked this, for the sake of making easier equations here. So let's see, V3 is over here. I have a 2K, I have 0 volts on this side. I'll work off the assumption that the voltage is higher at V3. For this current source, it's going to the left, so I might as well pick it to go to the left. I could pick this arrow to go in the opposite direction. There's nothing wrong with that, but I will have to pay attention to the polarity and say that it is minus 2 milliamps. That is if I picked my current arrow to go to the right. But I didn't. I picked it to go to the left in the same direction, so our polarity stays the same, 2 milliamps. Okay, and now up here on one side, notice that this wire up here goes into the 4K and goes all the way over to V1. So I have V3 on one side, I have V1 on the other side. If I look at the current going through here, now I can pick this to go in any direction. It makes no difference. I'm going to pick it so that it's leaving the V3 node. And now I need to go ahead and assign what these currents are. I will call this one IA, and I will call this one IB. Of course, remember that this IA and this IB are not the same as this IA and this IB. I merely am just reusing these variables for the sake of expressing my KCL equation. So let's go ahead and write out the KCL for this node V3. Easy enough. They're all leaving this node, so they should all cancel out. So IB plus 2 milliamps plus IA should all be equal to 0. All right, let's go ahead and write out what IA and IB are, and then we can backfill these equations. IA is going to be equal to V3 divided by 2K. And IB, make sure we pay attention to where this is going. I have 2 voltages involved. I have V3 on one side and this current going through the 4K. I have V1 on the other side. So let's go ahead and let's use the polarity to help us express the voltage drop across this 4K. This is a great way to never screw this one up. So I will say current always goes from a high voltage, positive, to a lower voltage, minus, and now I'll go ahead and say plus V3 minus V1 divided by 4K. Awesome. Okay, so I have my IA and my IB expressed in terms of resistances and voltages. Now let's go ahead, let's fill in this equation here, and I get V3 divided by 2K plus V3 minus V1 divided by 4K plus 2 milliamps equals 0. And now I'm left with my third equation. All right, so at this point, it doesn't fit. At this point, I now have 3 expressions. V1 is equal to 12, this long expression and this one as well. So once I fill in 12 volts into both of these, I am left with two equations where V2 and V3 are both unknown. Now, if you notice, this second equation here, once I put in 12 volts, I actually have V2. I can just straight up solve for V2 from this equation, and I can straight up solve for V3 in this equation. So in fact, I don't even have to do a system of equations for this problem. So this is actually kind of a nice, exam type question because you don't even need to solve a system for this problem. Once you go ahead and solve this, we are going to find out. Let me go ahead and redraw my example. So we have 12 volts. Two milliamps. 6K, 2K, 3K. And give me 1 second. Hello?
Hello, Eric Hernandez.
Yes, who is this?
So, Eric, my name is Jack from Canadian Park.
Sorry, I'm busy at the moment. Oh, those telemarketers. They're brutal. And a 4K up here. Okay, and we called this point down here 0 volts. Okay, once you solve those three equations, which are really just two equations, we are left with a V1, a V2, and a V3. V1 is equal to 12 volts, and you'll find out V2 was also equal to 12 volts, and V3 was equal to 1.33 volts. Okay, so let's go ahead and plug those in and see what's going on. 12 volts here, 12 volts here, and 1.33 volts here. Okay, so now we can go ahead and look at which direction our currents are actually going as far as our conventional current is concerned. This is 0, this is 12, the current's going down through here. Over here, this is 0, this is 1.33, that's higher. Current goes from a higher voltage to a lower voltage. And over here, current also goes from 12 volts to 1.33 volts. And over here, we have the same voltage on each side. So how much current are we going to have? Zero amps, because the voltage drop across this 3K is 0. So with 0 volts across a component or 0 volts across this resistor, we're going to get 0 amps flowing through it. Okay, but all of these others definitely have some current. 12 volts divided by 6K will give you the current here. 1.33 volts divided by 2K give you the current here, and so forth. In fact, any ideas what the current flowing through this 6K is without even looking at the voltages and applying Ohm's law? If you notice, I got a constant current source of 2 milliamps entering this node, and I have 0 amps going this way. So this better be 2 milliamps. Has to, if KCL is going to be correct. And if you notice, 12 volts is the voltage at this point. 12 volts divided by 6K is 2 milliamps. So 2 different ways of independently verifying that this is 2 milliamps. Awesome. Okay, and then over here, 12 volts minus 1.33 volts gives you the voltage drop across here. And if you are ever, a little lost with what's going on and you're like, well, how do I express the voltage drop across here? There's no reason to have to try and intuitively figure that out. Just tell yourself current goes from a higher voltage to a lower voltage and say plus 12 minus 1.33 volts. 12 volts. Let me calculate that out. 12 volts minus 1.33 volts gives me 10.67. So I have 10.67 volts across the 4K. So divide that by 4K and that'll give us the current. Okay. Let's go ahead and figure out what that is. 10.67 divided by 4K gives us 2.6675 or 2.67 milliamps. Okay, that's the current flowing through this 4K. Now notice I have 2.67 milliamps flowing into this node, and I have 2 milliamps leaving this node here. The sum of all currents entering must equal the sum of all currents leaving. So my good friend Kirchhoff, with his Kirchhoff's current law, says that this should be equal to 0.67 milliamps. 0.67 milliamps. I'm so confident in this that I'm actually just going to write it down before I even apply Ohm's law to see what it is. We're going to do 1.33, the voltage drop across the 2K, divided by 2,000 ohms gives us 0.67. Whew, okay. 0.67 milliamps. We're right on the money on that one. Okay, so this all works, and it works well, and it's a great tool for analyzing more complicated circuits. So with that said, let's look at another problem. Let me get some caffeine in me. I don't have enough yet. I think I'm on my 3rd cup of coffee. I woke up at 4:30 this morning with our new puppy licking my face and hand, and he just didn't stop for like half an hour while I was trying to sleep. And then at like 4:30, 4:45, I was just like, fine, I'll get up. Okay, let's go ahead. Let's make this one just have some voltage sources. We don't have to have current sources for nodal analysis to be applicable. We can do this on any problem, as we saw. Even our simple early on in the semester 211 problems were very straightforward to solve using this nodal analysis technique. So let's give ourselves, let's do a 12 volt source here. And let's give ourselves a 5K up here. Let's do a 1K over here and a 20K over here, followed by, let's do another one of these upside down voltage sources. Just be careful the electrons don't fall out. That's a joke. A bad one, I admit. But still a joke. Okay. Let's see. So, what did I draw here? I have plus down here, minus up there, plus down here, minus up there. First step, step number 1, assign the reference node. I can put this anywhere. Yeah, it is a good way to wake up, right? I can apply my my reference node. Sorry, not my non-reference nodes. My reference node or my 0 volts. I can take that to be anywhere. There's no reason that I can't have what is obviously the highest voltage of my circuit, which I would say is along this line, because I have my two voltage sources upside down with their positives connected to each other here. One's 12, one's 5. I expect that this would be my highest voltage point of this circuit, right? Current should be flowing in this direction, current's flowing in this direction. Everything's trying to get back to the minus side of that voltage source. But I don't care. Let's write it there. 0 volts. If what I've been saying thus far is correct, that it doesn't matter, then there should be no problem doing this. All right. So that takes care of step 1. Step 2 is going to be assign our non-reference node voltages. Here's a good one. V1. Here's another one that's got a different voltage than V1. So let's label it as V2. And same thing over here. This has a different voltage than everywhere else. So let's call this V3. I don't have to have current branching in order to call it a node in the case of nodal analysis. Any point. This is why I think a better definition for these nodes is any point that you have a different voltage is a non-reference node as far as solving this nodal analysis technique. Okay, so I have V1, V2, V3. Let's go ahead and let's get on to step 3. Let's write out what these voltages are. I mean, let's write out what these KCL equations are. All right, someone give me the KCL equation for V1. Yeah, V1's just equal to minus 12 volts, okay? Here's how we got that. I labeled this point as 0 volts all along this wire. So the other side of this 12 volts needs to be 12 volts lower than 0 volts. You with me on that? So if this is 0 volts, which is what I did when I labeled this as my reference node, if this is 0 volts, then the other side of this battery is going to have to be minus 12 volts. Okay? Let's go ahead and let's do the other super easy one. V2. Sorry, I meant V3. That is an ugly 3, but we'll roll with it. Okay, so again, the same thing as what we did over here. V1 is minus 12 because this point in the circuit is 12 volts lower than this point, and I called it 0 volts. Okay, so one thing to note, voltage is always relative compared to everything else in the circuit, and especially wherever I call to be 0 volts. If I call this to be 0 volts, then this is minus 12. If I called this point to be 0 volts, then this is going to be 12 volts higher than 0, so this would be 12 volts. So it's all a matter of what is it in reference to. That's why I'm calling this the reference node. Everything is relative as far as the voltage is. Everything is relative to this point being considered 0. Okay, so V3 is going to be equal to, well, it's 5 volts less than 0 volts. So V3 better be equal to minus 5 volts. Okay, let's get on to really the only elaborate one to write out for V2. So we'll start with V2. And to write out V2, let me box all these answers in. To write out V2, I'm going to have to pick some currents to help me out here. So let's go ahead and for the case of making the equation easier to write, I'm just going to pick my current going from what's assumed to be a higher voltage to a lower voltage. Now, as we saw, V1 and V2 and V3 are both negative voltages because they're relative to this reference node, minus 12, minus 5. Everything in this circuit is screaming to me that this is actually a lower voltage than this point, right? If this is 12 volts and this is minus 5 volts, this is all going to be lower than this point. And yet, when I write out this equation, I'm just going ahead and saying, well, this current goes down. And there's nothing wrong with that. The problem is still going to work out because, as you'll find when we solve this, you'll end up getting a negative value, and that means the actual current is really going in this direction. But for the sake of writing these equations, no one cares. I can just pick this to go down. It makes writing it easier, so I might as well. Now, these other ones, oh man, I have negative 12 here, negative 5 here. Should I pick this to go to the left? Should I pick this to go to the right? Doesn't matter. Not overthinking that one. I'm just going to have them all leaving. And then I'm going to label them IA, IB, and IC. All right. IA plus IB plus IC should all cancel out and equal 0. Now let's write out what IA, IB, and IC are. IA, again, I will use my current to help me out. Goes from a higher voltage to a lower voltage. Plus V2 minus V1. All divided by 5K, invoking Ohm over there, Ohm's law, and that gets us IA. IB is just going to simply be V2 divided by 1K because I drew my current as going from a higher voltage to a lower voltage. IB is going to be V2 divided by 1K. And IC, well, again, I have two voltages, so let me use my polarities to help me out here. Plus, minus, plus V2 minus V3, all divided by 20K. Oh, I will move myself out of the way on that one. All right, let's go ahead and plug all of these in. And I get V2 minus V1 divided by 5K plus V2 divided by 1K plus V2 minus V3 divided by 20K is all equal to 0. And now I have my third equation. Nice thing about this one, again, I don't have to solve a system because I already know V1 is equal to minus 12. So propagate, plug that all into this equation. Same thing with minus 5 for V3. So put in a, this is going to end up being, well, plus 5. And this over here would be plus 12. And go ahead and solve for V2. Well, V2 ends up being equal to minus 2.12 volts. All right, so I have my three voltages, V1, V3, and minus 2.12. At this point, all of this work was just for finding these three values. Once we have these three values, I don't care about this equation. I don't care about these current directions. I don't care about any polarities that I wrote down. So let's go ahead and let's rewrite this and see what's going on in this circuit. I think it's safe to move myself back down here into the corner of the screen. Okay. V1 I found to be minus 12. Actually, let me write in the resistance values. 5K, 1K, 20K. And over here, I found this point to be minus 12 volts. And I found this point over here to be equal to minus 2.12 volts. And over here, I found this to be minus 5 volts. Of course, that was all under the assumption that this was 0 volts. Well, no problem with this. Let's see, what is the current doing? Well, current always goes from a higher voltage to a lower voltage. So it goes from this point to minus 2.12. Again, current always goes from a lower voltage to a even lower voltage. And current goes from a low voltage to an even lower voltage. And if you want to figure out what my current is, let's look at this 1K. Well, how do I do that? I mean, I can just look at this and I can tell you what's my voltage drop across the 1K. It's 2.12 volts. Is it minus 2.12 volts? No, absolute magnitude. It's just the voltage drop across it. So 2.12 volts is what I got across this 1K. But if you're ever stuck, if you're ever confused by these polarities, if you're ever kind of, a little disoriented, just use polarity to help you out. Current goes from a higher voltage to a lower voltage. Plus 0 minus a minus 2.12 volts gives me my voltage drop of 2.12 volts. 2.12 volts divided by 1K gives me 2.12 milliamps. 2 zeros followed by, 2.12 milliamps. Okay, let's look at this one. Again, I got negatives all over the place. I may be disoriented. You know what? Current just goes from a higher voltage to a lower voltage. Let's go ahead and say plus a minus 2.12 volts minus a minus 12 equals, well, minus 2 point, I don't know what's going on. Let me use my calculator. Minus 2.12 minus a minus 12, so plus 12. A, 9.88. Okay, 9.88. That's the voltage drop across the 5K. So 9.88 divided by 5K equals my value of current. So 9.88 divided by 5,000 gives me 1.976, 1.98. Okay, let's look at this last one. Again, I have minus 2.12 and I have minus 5 over here, and I'm lazy and I don't want to overthink this, so I'm just going to put a plus here and a minus there, and I'm going to say plus a minus. Minus a minus 5. Okay, what do I have there? Minus 2.12 plus 5. So minus 2.12 plus 5 gives me 2.88 volts. Okay, that's my voltage drop across the 20K. So let's take 2.88, divide it by 20K. I'll just squeeze that in over here on this side. 2.88 volts divided by 20K equals 0.144. Okay, I took that one out to 3 decimal points. I took the other ones out to 2 decimal points. Let's see how close we are. Okay, the sum of all currents entering a node, specifically this node, is 2.12, and the sum of all currents leaving that same node is 0.144 plus 1.99. I really hope that that adds up to this. 1.98 plus 0.144. All of these are milliamps, equals 2.124. Perfect. Okay. So if you notice, even when you start getting, negatives and positives and more negatives and double negatives, and they're all floating all over the place, you can always just rationalize and make sense of it and rely on what you know. Rely on these statements. There's a reason that I keep repeating current goes from a higher voltage to a lower voltage. That is a fundamental truth for all of your electronics. That guide is never going to let you down. It's like a map, right? And yeah, that's everything we need for this circuit. Okay, so cool. Yeah, once you have that, you know everything there is to know about this circuit. Do I have any questions about this? I sure hope that mesh analysis and nodal analysis get you the same answer. Yeah, absolutely. They will. They will. For sure. You know what? I've seen these types of problems. So, and I got to switch between academic mode and practical mode here. From an academic sense, when you're looking at, these are problems that do nothing. These are problems that their sole purpose is to help you learn about these techniques. There is no circuit I have come across that looks like this at the workplace. And so when you're looking at problems like this, yes, one technique is going to be easier to apply than another technique. Or maybe they're both as convoluted, or maybe they're both as simple. Generally speaking, when I come across these types of academic problems, I will find that, mesh analysis looks like it might be easier, and so I apply it just for funsies. And then I go ahead and I'm like, well, what happens if I apply nodal analysis? And then I apply nodal analysis. I was like, oh, MG, that was really easy, right? So there was a problem. I used to give a problem on the final, and it was like this. It was one of those just really made you think when you were using your basic rules. And then I had a student come to me later that wanted to like just work on this problem. He found it interesting, and it was one of those problems I just made up on the fly. And he was like, well, what about if we apply mesh analysis? We were in my office, and I went to the whiteboard in the office, and I said, yeah, let's apply mesh analysis. Let's see what happens. We applied mesh analysis, and it was easier than just using your basic rules, because you didn't have to, think as much about parallel series, combining resistances, that. So it was more of a procedural approach to finding it, which makes sense. Mesh analysis and nodal analysis are more programmatic and procedural than all of our earlier basic rules, because when you're solving a big circuit using just basic fundamental rules, you kind of there's no one guiding you along the way. You sort of have to look at the problem and go, well, I know this, I can solve for this. Okay, what else could I solve for? Well, I'd have to figure this out before I could, and so you have to kind of invent your own path as you navigate that problem when you're just using your basic rules. But when you're using mesh analysis and nodal analysis, I just follow steps and I come up with an answer. So from that aspect, it is very convenient and nice, but ultimately it might be a little longer with the results that you get, and so you trade off the simplicity of navigating the problem for a little more complexity in solving those systems of equations. And so going back to this story, he was in my office. We went over the problem. We did it with mesh analysis. Sure enough, without having to think about the problem too much, we got the right answer, and it matched what we got previously. And then he's like, I wonder what would happen with nodal analysis. I was like, I wonder what would happen with nodal analysis too. I never tried it. So we applied nodal analysis. We ended up with like one equation, one unknown. And I was just like left scratching my head like, man, that was super easy. I'm like, if you know these techniques and if you apply them, you can start to see that some of these techniques are going to work better in some cases than others. And this was a perfect example of a problem that I had never thought about applying nodal analysis to. And once we did, it was just very simple and much easier than mesh analysis. Now, that being said, that's kind of the academic sense. If we take this to more of a practical sense, I'll give you, without going into, what this circuit is, or even there's going to be a component in here that we don't know what it is. It's a transistor, but we really don't know. I haven't taught anything about transistors, and we'll see that in 311. But let's go ahead and take a problem like this, where you have one component we don't know about yet, but it's called a transistor. We'll learn about it next semester. And we have these 4 resistors here, and it looks like we have this voltage divider over here, and we have this resistor below the transistor and this other one above the transistor. Now, this is incredibly practical, insanely practical. But how do you solve something like this? That's where we don't have time to, relearn and learn basic rules. We kind of need to accept these things as truths that we've been learning. And as it turns out with this problem, I have a reference node here. I have a voltage applied here. I can write out what this voltage is in terms of these currents, and I can do this all throughout the circuit. As it turns out, applying nodal analysis to this portion, but just this portion, ends up making this problem that really couldn't be solved any other way all of a sudden solvable. Now, as it also turns out, you can form a really good approximation for this circuit using a Thevenizing technique. So you could Thevenize this front half and simplify it to something else. So, but that's the thing. We kind of need to nerd. We kind of need to learn these techniques before we can see where they are practically applied. So I can't just give a practical circuit and say, hey, we're going to learn about nodal analysis using this, because there's so much more going on. And the nodal analysis is only applicable to one portion of this circuit. You don't need to use nodal analysis for the rest of it. You just apply it here. So ultimately, a more elaborate nodal analysis problem in a practical circuit can actually be simpler because you don't have to apply the whole thing. But for the sake of learning, we got to start with circuits that are interesting for the technique that we're learning, not necessarily interesting from a practical point of view. So, that's my. Is it a shame to me that every circuit that we, have seen is not, 100% practical? Yeah, but it's interesting enough for learning the techniques that we can then apply to the practical circuits. So I'll go ahead and leave that monologue there. So any reason to choose one over the other? Only experience is going to teach you that. Only experience is going to teach you that. There's too many variables going on. And like I said, there's many times where I don't see that one would be more applicable than the other. If I come across a circuit I've never dealt with before and I start analyzing it, this was true. I added some sections to my 311 class. I was working on that, and I didn't see right away that one technique was better facilitated the problem than another technique. And so I was kind of like just sort of running into a wall, brute forcing it with one technique. And then I looked it up, and it was just like, oh, this is super easy if you apply this. And I went ahead and did it, and I was like, oh yeah, that is really easy. I'm like, why didn't I think about that myself? So it comes down to experience. Okay. Let me go ahead and stop the recording at this point.